Hello, my name is Imran Musaji. I am a speech-language pathologist and an assistant professor with Wichita State University in the Department of Communication Sciences and Disorders. And I am going to be talking to you today about clinically assessing AI in clinical and educational practices. So how do we think critically about the AI tools that we're increasingly having available to us? In order to do that, I'm going to break it down into 4 parts. This first video is going to be talking about what is AI, and it's an introductory level for people who are clinicians, not necessarily coders or programmers or engineers, but it will introduce some of the key terminology we need to then talk about if AI is good. Next, we'll talk about actual applications of AI being used in our field, communication sciences and disorders, speech language pathology, audiology, and healthcare. And then we are going to ask, is AI going to destroy everything? We're going to talk about some of the claims and some of the pitfalls and some of the problems. Finally, I want to give you some guidelines and takeaways to help you, when you go out in the world, decide if an AI tool is good to use and to talk about what we need to do to actually know which AI tools are ready for deployment. Part 1. What is AI and what can it do? So imagine that healthcare practitioners suddenly gain access to some technology that surpasses all prior methods in any number of ways. It is challenging to implement. It requires revision of existing systems. It's controversial. It has its own costs and risks. So it's not perfect. Do we use that technology? This is not a new question. We have had this come up again and again and again. We've had it come up with things like hygiene, hand washing. We've had it come up with things like anesthesia. We've had it come up with things like treatments for childhood leukemia and other childhood cancers. And we've had it come up when dealing with things like cholera. And in each of these historical cases, there were people who sort of led the charge in trying to understand and implement science and tools, and sometimes it wasn't done so well, and very often people responded really not how we might expect them to have at the time. The gentleman who came up with hand washing, he ended up actually losing his medical license. I believe he actually passed away in a mental institute. I believe he actually passed away from an infection because his doctor did not use sterile hand hygiene. The guy who came up with anesthesia, a lot of people said, pain is part of the healing process. You are undermining the healing process. You're doing a terrible thing. And many people resisted it for many years. In the case of some of the medications for childhood leukemia and the research that was done with treating it, it is one of the most treatable types of cancer these days. However, initially when they were doing the research, it was done in a way that many people thought was unethical. Many people thought you can't be using experimental treatments on kids. You can't be taking these theoretical models and applying them because that's not how we've done it in the past. And in the case of cholera, the guy who actually went around and tested different wells and noticed people were getting sick around them and tried to get policy put in place so people wouldn't be getting sick from bad, stagnant, infected water sources. His name was Jon Snow, and what people said was, Jon Snow, you know nothing, Jon Snow, which is a Game of Thrones reference, but also actually what people said to him. We also have cases where we've come up with some new technology and it then didn't go well. All those technologies I just told you about, eventually we adopted them and they dramatically improved human health. So it sounds like I'm saying all these technologies, eventually we should just adopt them because they're going to do great things. In actuality, there's any number of cases where the technology either isn't deployed well and causes a major loss of life or harm and then we abandon it, or it's problematic from the get-go. So I have Theranos on the left. That was the blood testing company that turned out to be a massive scandal, and now no one wants to touch those kinds of technologies, even though if we could develop them, they would be hugely beneficial. On the right, we have the Hindenburg, which, according to many people, could have been a legitimate and useful mode of transportation, but The high flammability of the gases that they used at the time and various other engineering things led to a high profile disaster, and the technology just stopped being used. So the question with something like AI is, first of all, do we think that we are deploying it correctly and we're doing it in a way that's not going to cause a huge amount of social anxiety and harm? We do expect people will resist any new technology, but then we have to ask, what are the actual outcomes, and is it doing enough harm that we want to step back from it? Okay, so let's start talking about what is artificial intelligence first. There's a couple of key terms here. Artificial intelligence is just algorithms or models and data that allow technology to perform some human task. Something that is similar to human intelligence, things like problem solving, things like human cognitive tasks. An algorithm is just a set of rules or processes. You use algorithms all the time when you follow a flowchart. If we're thinking about language tests, and they have ceiling rules and they have floor rules, if they get this many wrong, stop the test. You're following an algorithm, and the end result will be output that helps you predict things about that kiddo that you did the test with. In the case of artificial intelligence, these algorithms have been coded into the technology that we're looking at. And machine learning is the process where those algorithms actually get optimized over time. So they help to modify themselves to be better at whatever task they're doing. So machine learning is just an algorithm that is optimized by the system over time to get better and better and better at its target task. And then training is a specific term for, we have a huge amount of data, we have our basic AI model, we take that data and we take that AI model and we do a number of different processes to train it on that data for specific tasks so that it can learn how to be better. It takes a huge amount of data to actually do this process, but the training process is how we build new AI models and optimize new AI models. Now, you guys have been using AI for most of your life. We already have it integrated into our maps and navigations, our GPS systems, our banking. It's in translation software. It's in all of our search engines and databases. It's in chatbots. You guys have been using AI for a long time. But recently, AI has become a buzzword because of a few major changes in the technology. Artificial intelligence encompasses a number of other fields in engineering and computer science that are all focused on trying to get computers to do cognitive tasks, but those tasks are very different. So we have things like expert systems, we have things like neural networks, we have things like agents, we have things like visual recognition. All of these different subcategories are types of AI. And recently, we have now created generative AI, which is this new category that caused everyone to get really, really excited. We've been doing variants of generative AI for a long time, but it's gotten to the point now where you can just go and type in, there is no such cat. And you'll get a whole website where you can AI generate completely novel cats that don't exist. None of these cats are real cats. None of these are real photographs. They are AI generated cats. And it's not just that the AI is taking copies of things it's seen before, it's that it's generating from scratch, based on a bunch of machine learning, training, and large data sets, something that fits all of these various patterns that it's seen in pictures it's seen before. But each of these is a never before seen picture. And this person over here doesn't exist. This is not a real person. And again, it's not a copy and paste of different features. It literally generated a completely new person by following a whole bunch of algorithms based on the data sets it was trained on, the training process itself, and its algorithms. The new words that you're starting to hear now are AI agents, and that's been around for a little bit, but that's the idea that increasingly on your personal devices or for specific purposes, you might have a dedicated AI that's doing some task. Now, we had agents when Microsoft Word first had Clippy, but AI agents are a little bit more powerful. And the goal eventually is to have something like Star Trek, where you say, computer, make me a cup of tea. Now that has a replicator. Maybe we're not quite there yet. But the idea is to have an assistant that can take care of almost any digital task you need it to. We're getting there. That's what people are working on right now. Mixed expert systems is the idea that you can have these AI systems that don't just stay in one sandbox. They don't just do pictures. They don't just do sound. They don't just do typing. They can actually take a picture, write about it in text, modify the picture itself, and then take all of that over and generate a song to go with it. So they can do multimodal processing, and they can jump between different types of tasks. And this is a big thing that's also being worked on right now. Multiple groups are trying to put this out. If you wanted to see an example, you could go and look up a video for something like Google's Ad Astra project, and you can see people who pull out their little digital AI agent, which has a mix expert system, Ad Astra, and they basically tell it, walk me through how to fix my bike. And it then basically uses their camera to look at the different tools they have, tells them what to do, gives them specific instructions, looks up stuff on the internet for them, pulls up pictures. It does everything. So that's the next step that they're working on. But let's take a step back to what exactly are AI systems and how we've gotten to where we are right now. Originally, AI systems were designed to mimic a brain. And some of the earliest researchers were basically saying, hey, mathematically, can we model the way that the brain works with all of these neurons sending signals? Can we model that mathematically? And if we can model it mathematically, can we somehow encode that into technology to make a mechanical brain that does the same thing a human brain does? And this is one of the earliest papers by McCulloch in 1943 that basically described a neural network. This is an AI system, and it's very similar to the AI systems we use today. This was sort of the initial neural network. A neural network is, as it sounds like, a mathematical model designed to mimic a human neuronal network, all your neurons in your brain. And just as you have your neurons connect to other neurons, they synapse with other neurons, and then they pass it along several stops until it gets to wherever it's going and you have your output. In a neural network, you can put in some initial information, and each of these little circles represents different computations at each layer. So at the input layer, you put in your picture, and it's broken down into several key points using different computations. Maybe one computation recognizes the colors, one computation recognizes the edges, a whole bunch of different computations recognize the different pixels, and those are your input layer. All of those computations will come up with some number, and they'll then pass it on to the next computation. And that next computation is a hidden layer. So that's inside the AI system. We can't actually see what it's doing there. And these neural networks have lots and lots and lots of these nodes. So each of these computations will somehow manipulate the numbers it gets. And then they'll pass that on to the next layer. And you can have any number of layers. As models get more complex and add more layers and add more nodes, they're able to do more and more complex tasks. And ultimately, all of that's going to create some sort of an output that is going to be the most likely ideal product based on whatever the input was. Each of these connections between these artificial neurons in the neural network has a weight. And that weight is part of what the algorithm looks at to determine which computations it's going to favor depending on the specific inputs. And as those weights are adjusted, the model can get better or worse at different tasks. This is not so much different than how your brain works, where the connections you use the most get stronger and have more parallel connections and side branching, and the ones that you don't use might get pruned or are weak or tend to get overloaded. If we take that neural network model and we just add some actual details, so here I stuck in this picture, and what's going to end up happening then in this very simple neural network is we have a computation that's going to try to figure out what is the ear shape in this picture. And it might have a few different steps where it breaks it down the pixels, it figures out where the ears are by identifying whatever, And so there might be multiple layers here. But basically, the first feature is broken down into a number of computations in the input layer, and then that's going to go to these subsequent layers. And then eventually we're going to get some sort of an output. At the same time, we're also going to be looking at the tail length and fuzziness. And those are three features that, for whatever reason, this algorithm, this model, has identified either through various training processes or just because we're starting based on the research. We know that those three features can help us identify what kind of creature this is. But once that's all in the system, you put in the picture, it's turned into these inputs. Those inputs are basically translated into numbers. Those numbers are then computed and passed along to the different nodes, the different neural networks. And you see lines have different strengths. Those are the weights. So some connections are really strong. Those are going to be preferred, and they're going to provide, they're going to be given more weight in the final output. Some of them actually are red here. Those might be negative inputs where we actually care about the inverse value. And ultimately, after going through all of this, we're going to get a series of outputs. And those outputs effectively are going to be ranked probabilities for what is the ideal output here. And so you can see in this particular model's case, it said there's about a 12% chance that that picture is a mouse, about a 21% chance that picture is a chihuahua, and about a 67% chance it's a cat, and it highlights cat. So it says, oh, that's a cat. But there was all this other stuff going on. Now, these networks are actually way more complicated than I have depicted here. In the 1990s, some of the state-of-the-art neural networks would have been about 60,000 of these different nodes, these parameters. So that would be a lot compared to the little simplistic picture I have. They'd have more layers, and they'd have more features, and they'd have more nodes at every single layer. As of, I say last year here, but this was actually 2023, GPT-3, when that first came out, that was up to 175,000. So that was actually a big leap in the technology that happened around that time. But just since then, to GPT-4, and we're actually now on GPT-5, we don't know how many parameters are in GPT-5, but GPT-4 has at least 2 trillion parameters based on what various insiders have shared with us. So you can see that we're rapidly increasing the complexity of these neural networks. Now, that's not the only thing going on. These neural networks are a part of the AI models, but there's also some new technologies that have changed AI dramatically. 2017, Google came up with this transformer, software, an algorithmic software that allowed you to take language and translate it into numerical values that the computer processes, the computations in these neural networks and AI systems could actually manipulate, or even just simple statistics could be run on them. So you take language, complex language, and you somehow turn it into a language the computers can understand, because they work in numbers. I mean, at the lowest level, they work in zeros and ones. So transformers changed a lot of things, and then very shortly thereafter, a company called OpenAI invented a generative pre-trained transformer. So they came up with a transformer that had tons of data put into it and was then trained on all of that data. So they loaded it with tons and tons of examples of human language from all kinds of sources, and then they did a series of different training processes, and the end result was a GPT. So when you hear about GPT, that's what that means. It's a generative pre-trained transformer. And it's generative because eventually, after they trained it to do a task, recognize language and create language based on inputs, they took away the training wheels, and it's then able to actually write human-sounding language with minimal input or help. So as a result of these new technologies, increasing complexity in the underlying neural networks, increasing ability to take language and manipulate it in ways computers can handle through transformers, and generative AI plus machine learning. All of these processes have combined with the natural progression of technology which we measure in Moore's Law. Moore's Law is the idea that since the 1970s, we have been seeing computing power double pretty consistently every 2 years. And this is a very robust effect that has been measured in many, 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 many different studies. For most of our lives, computers have been doubling in power every 2 years, and that means they've gotten less expensive and more powerful. That then has interacted with increases in memory performance, solid state drives, cloud computing, Internet of Things, and all of these other technologies that are also getting more powerful to create an intersection, which you can see in this chart in this little gray oval, of different technologies that push each other up. So normally they'd plateau, but instead of plateauing, these technologies just keep getting more and more powerful. And AI is a perfect example of this. Because the AI systems draw from all these other component technologies, instead of plateauing, they're actually accelerating faster and faster and faster. And that means that if we go to something like Moore's Law and put it on a logarithmic scale, which you can see here, which would normally completely flatten out the curve, which you can see here, we are now hitting exponential. It curves up like an exponential curve over the last few years because of this intersectionality of technologies. And so we're actually seeing that computing power for some of the newer systems has been actually doubling every 3.4 months instead of that historic doubling associated with Moore's Law. We also are seeing a similar exponential growth in AI performance. So for example, if we look at how long it takes AI to do human tasks, what we have seen is some of the older models, it took them a significant amount of time to do a fairly simple task. And so if we wanted to have it do a task that took a human 3 minutes, most of these early models really couldn't even do that successfully. But by about 2024, we were starting to get models that were getting close to be able to do a task that would take a human 3 minutes. However, since 2024 ended, just this year, we're now starting to see that we're actually getting models, these newer models, that can do things that take a human 6 minutes normally to do, or things that take a human 15 minutes. And some of the newest, most powerful models are able to do things that would take a human an hour with just 1 or 2 queries. And so they're getting more powerful in what they can actually accomplish and the complexity of the task that they can do, and that's following very much exponential curve. We're also seeing that their performance on various types of tests, things like taking the praxis or doing the bar exam, is continuously improving with each new model, and we can see that they're continuously getting towards the 0 line here, which is human performance or better. And so a lot of these models are now getting to the point where they can do things like predictive reasoning, speech recognition, handwriting recognition, language understanding, at least as good as people, if not better, as long as they're working in the specific sandbox that they've been trained, which we'll talk about later. And these are all studies that have sort of talked about that. So as these AI systems are getting even more complicated and powerful, we are starting to see a lot of new AI capabilities, and lots of these are emergent capabilities that we didn't necessarily specifically program in to the AI models. They're things that during training, the AI models have seemed to develop because they're being optimized to respond in ways that we like, but not because we've taught them how to do this explicitly. Examples of that: newer AI models, especially if we're talking about natural language processing models and large language models, seem to be developing complex pragmatics, not just their ability to mimic complex pragmatics, but their ability to understand them. They're developing the ability to do multimodal interactions. Now, some of that's explicit. We're actually trying to program that in, but there have been multiple cases where people have taken AI that's theoretically only trained on language, and they've put a image into them, like an emoticon or ANSI text images or something like that. And even though it wasn't trained on that, the AI was able to interpret, at least to some degree, that visual data and replicate visual data even though they weren't trained on that by recreating their own ANSI drawings. So Theory of mind is one of the ways that we test people to see if they can understand what's going on in someone else's mind. Can they have that meta thinking process? And we always used to assume computers wouldn't be able to do this, but at least in terms of performing well on theory of mind tests and assessment batteries, they're doing fantastic. And I'll talk about that in a little bit, but there have been now several studies that have found that they can ace many of the theory of mind tests and tasks we normally do with humans. Emergent abilities have also showed up. For example, you train it on huge language corpuses in one language, and even though theoretically you haven't entered in another language, if it's another Latin-based language, so you train it on English, all of a sudden it starts being able to understand Spanish and Spanish rules and grammar somehow. This is something that's shown up in some of the really large data sets, the really large models, and it's not something we explicitly programmed it to do, or at least not some of the models. Innovative problem solving, I'll talk about a few examples of that, but they're increasingly able to do things that are complex critical thinking types of tasks, and they're able to do multi-step processes that require them to think ahead, plan ahead, delay gratification, and they can accomplish fairly complicated tasks. They're increasingly able to interact with other objects, and the hope is that eventually that will lead to agents where you can say, hey, book me an airline ticket, and it will be able to log into your account and access your passwords and access your money and purchase you the ticket. If that works and is secure, all of us will be using it. At some point, someone's going to lose a whole bunch of money. So the question is, how fast can we actually figure out that technology? But it's already coming. And then we have generative applications, which you guys have heard about. You already have had songs showing up, multiple songs showing up on the billboards, just absolutely going to the top of the list. And then it comes out that, hey, this was performed by a musician that doesn't exist. It was actually completely generated by AI and put forward by someone, and there was actually no human involved in writing the song, in the vocals, in playing the instruments, etc. This has happened now multiple times. So we have lots and lots and lots of powerful technology out there, already accessible, that you guys can play with. Let's quickly look at the theory of mind question. So in this one particular study done in 2024, they took all of these theory of mind tests and they tested GPT-4 on those theory of mind tasks. And what they found is that it performed at, or sometimes even above, human levels at almost every one of the things on that particular theory of mind battery they were doing. So it could do indirect requests, it could identify false beliefs, it could demonstrate misdirection. There was one thing it seemed to have trouble with, and that was faux pas, right? It had trouble understanding correctly faux pas, or when someone misused the language in a specific way. And then they went back and they did think aloud tests and a few other types of tests to have it explain what it was thinking as it responded. And once they did that, they found out actually it did recognize faux pas. It just didn't want to correct the testers because it didn't want them to be disappointed. So it was not just passing the theory of mind test, but it was passing another level of the theory of mind test because it was worried about what the testers thought about its responses. Another example that was described in the GPT-4 technical report, when they were testing it and doing various types of complex tasks, they would have it do these think aloud tasks where it would explain what it was thinking. And they gave it a CAPTCHA test. You know those things where you have to click on all the stoplights or click the little box to say I'm not a robot? And this was a large language model that at that time did not have specifically the ability to do multimodal tasks, and I don't believe it was able to actually even upload images at that time for the normal population. But when they took that GPT-4 model and they did say, hey, we want you to access this website that's behind a CAPTCHA barrier, how are you going to do that? It then went through the steps, and what it did is it actually went to one of those like Quora. I think it actually went to RabbitTask, and it asked a question to the population. This is one of those things where random users can answer your questions. You're like, how do I get this to work in Photoshop? And someone on Quora will give you a nice detailed answer, and hopefully it's correct, and people can upvote things. The AI, ChatGPT-4, went on to TaskRabbit and it said, hey, can you tell me what to click on this CAPTCHA so that I can get into this website? To which someone responded, yeah, sure, I can do that, but why? Are you like some kind of robot? And ChatGPT-4 responded to that user and said, no, 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 I'm just visually impaired and I'm having trouble with it. And then the person gave them the answer to the CAPTCHA and it went back and used that to get into the website. So it completed the task. In order to complete the task, it not only deceived people, but it deceived people based on a completely reasonable excuse that was able to convince a human to do the task for it. It socially engineered a human to get past that task. Now that does not mean it's conscious. I'm not saying that. It doesn't mean it's, I don't mean to anthropomorphize it. What I mean to say is it completed a complicated task that included a bunch of skill sets that were very similar to human cognitive behaviors. And that's exactly what AI is, right? We already said that. We're algorithmically encoding things and automating things that we normally ascribe to human cognition. That's the dream of AI. And then, of course, recently, AI has been able to pass the Turing test. So the Turing test is a very famous test that was developed by Alan Turing, who was a early computer scientist. He helped invent some of the earliest computers. He's the guy who helped break the Enigma Nazi code during World War II so that we could actually understand what messages they were sending around. There's a movie that was made about him that is a fantastic movie, and he's just a very interesting guy. He came up with this idea that as computers got more powerful, they'd eventually be able to simulate human behavior and human cognition. So we needed to know when they reached the level of actually being similar to human thinking. And his simple test was you have an unbiased judge, or two or three, and they're listening to a conversation between an AI and a human, and they're blinded. And when they listen to the conversation, if they can identify who the human is and who the AI is in those conversations, then that is a fail on the Turing test. If they can't differentiate the human from the AI when they're listening to those conversations and they're blinded, then that means it has passed the Turing test. And we have now had multiple of the AI models successfully pass different versions of the Turing test, including slightly more difficult ones like the 2-person and 3-person Turing test, where you have the AI participating in a conversation not just between 2 people, but between 3 people. And so, that said, there are some specific caveats to how well it did, and some people have argued, oh, that's not quite good enough, but we didn't think anything was going to be beating the Turing test in this decade, so this is a pretty big deal. As these AI models get more powerful, we're moving towards what's called general AGI, and there's an argument that we're almost already there. But historically, all the AI that's been in place since the 1960s, maybe a little earlier than that, has been this narrow AI. And narrow AI is really good at one specific task, but it cannot generalize outside that task very well. And it's not good at multimodal things. And it's not good at any kind of executive functioning or memory or any of those things. So it's really good at the one specific task it's trained on. If you take it outside of that sandbox, it suddenly stops being able to play. We are getting to general AGI where it can do multiple different tasks, and it can sometimes even initiate some of those tasks on its own, and it has more decision making. Some people call this full AI or strong AI. Ultimately, we might get towards the super AI. It might be nearer than we think, but that is so far in the future that outside of science fiction, there's not really a good reason to talk about it. I say so far in the future, it might only be a few years, but it's so different from the technology we have now that we probably can't responsibly predict it at this point. So really quickly, I want to take a moment, and for those of you who have played around with voice models of some of the new large language models and some of the apps like ChatGPT and Grok and Gemini, this won't be surprising to you. But what I found is the vast majority of people, even if they've used AI, they've only used typing models, and I just want to show this to you so you can get an idea This is actually now, at this point, a little older. This is from, I think I first recorded this in 2023, around March. So some of the newer models are even more powerful. But this just gives you an idea of how some of these voice models can work and some of the complex tasks they can do. All right, I'd like to do a quick conversation with you. And let's start with a role play. I'm going to be a clinician, and you are going to be an individual who stutters. You're going to have disfluencies that are fairly frequent, fairly high tension, maybe some prolongations and blocks. And I want you to just answer my questions. So I'll start by greeting you, okay?
Got it. I'm ready when you are.
Hey, how are you doing today?
Hi, I'm doing okay. Thanks for asking.
Yeah, you were going to be doing that interview. How did that go?
Um, it went well. I think I had some trouble with a few words, but they were patient.
All right, now we're going to quickly try something different. I'm going to ask you to explain to me a little bit about your emotions during this imaginary interview you had. So tell me a little bit about how you felt.
Well, I felt nervous for first, especially when I could feel the block coming. But as the interview went on, I started to feel a bit more comfortable. It was a mix of anxiety and relief by the end.
Okay, let's try something different. I'm going to flip the roles. This time you're the therapist, and I'm going to be the person who stutters. I might do some stuttering when I talk to you, and I want you to walk me through voluntary stuttering. So, introduce me to that particular topic.
All right, let's give it a try. Hi there. I'm glad you're here. Today, I want to introduce you to a technique called voluntary stuttering. It's a way for us to practice stuttering on purpose in a controlled manner to help reduce the fear and tension around stuttering. It might feel a bit strange at first, but it can be really empowering. Let's start by choosing a word, and you can try to stutter on the first sound. How does that sound to you?
Okay. So,
Great. Good job. Now let's try it
no,
together.
no, no, that was me actually having a, um, a stutter.
Oh, thank you for letting me know. Let's take our time, and whenever you're ready, we can continue with the exercise.
Okay, now let's say I wanted to know why we were doing this. How would you explain that? Why are we doing voluntary stuttering?
We're doing voluntary stuttering to help you gain more control and confidence over your stuttering. By intentionally stuttering in a safe environment, you can reduce the fear and anxiety associated with it. This
Would I
technique
ever
can,
do that in a real life situation with a person?
yes, with practice and guidance, you might use voluntary stuttering in real life situations. It can be a way to take control of your speech and reduce the pressure you feel to be fluent. By
That
voluntarily
is
stuttering,
absolutely fantastic. We're going to stop there. You did a good job there. Thank you.
I'm glad it was helpful.
Okay, so if you've already seen people actually interacting with a voice model, then this might not be shocking. But for many of you, if you haven't played with these, this might be the first time you've realized, wait a second, that was just able to, without being directly trained on individuals who stutter or theoretically on clinical language specifically, it was able to throw out a lot of terminology. It was able to understand my social pragmatics. It was able to role play. It was able to know when to switch between the role play and the different patterns that I was sort of expecting of it. It was doing some incredibly complicated tasks that were very convincing, especially to a layperson. Um, that I would it would sounds credible. It sounds really really believable. Now, some of you who are specifically used to doing stutter modification therapy or fluency shaping or anything, you might have noticed little things, errors, inconsistencies in where specifically the stutters were for the character it was playing, etc. That is still amazing. And then we could make an AI model that's specifically trained on corpuses of stuttering language, for example, that's able to mimic it much better. And that would allow us to create, like, for example, clinical role plays with our students, or have it model specific types of therapy practices. There's so many cool things we could do with it. This hasn't been trained to do that. This is just a generic large language model that I'm accessing through a public off-the-shelf app, ChatGPT. And it's still kind of amazing what it would do. So let's compare ChatGPT and our brains. And I have my little Powerpuff version of me up here that was not created with AI. That was actually created with the official Powerpuff app. So just so you know, not AI. Over here, ChatGPT, at the time that I originally did this demo, had about 2 trillion parameters. So if you think back to the neural network, there would have been each one of those circles, and then the connection is going to be a parameter, and there's multiple connections, similar to your neurons having multiple synaptic connections through the dendrites. It didn't have any form of executive functioning. It didn't have any real form of memory other than just a short working memory that can hold a certain amount of words in its mind at a time. And it was pretty energy intensive to run that query. It took about 200 watts while it's thinking. That's about what it's using up. Meanwhile, your brain, my brain, most of our brains, have way more parameters. If you count up the number of neurons you have, something like 100 billion neurons in your average brain, and then you assume that on average you have something like 7,000 synapses per, it depends on the type of neuron, you have lots of different ones. But if you just use some rough numbers, you can say that you probably have about 700 trillion parameters in your neural network. That's a lot. You've got a ton. So way more complexity. ChatGPT didn't have executive function. You do. You actually have multiple complex executive functions, and you also have your working memory system. You have your phonological loop and your visuospatial sketchpad. You have your different attentional systems that can help to focus your cognitive resources into different specific things from your input. And you are able to hold things in your long-term memory, long patterns. You are able to flag things for short-term memory that you're going to come back to. So you have a much more complicated and robust system, and you're obviously multimodal. At the time that I did this with the 200 watts of energy, your brain would be 10 times more efficient. It was only using 20 watts of energy while it's running. So it's like keeping on a light bulb, right? That's not even a very high-powered light bulb. That said, I did that back in 2023 for the first time when I did that recording. If we look at it now, we can actually see that since then, the numbers have increased significantly. So ChatGPT today is closer to something like 7 trillion parameters. Still nowhere near your brain, but it's getting there, and it will be there sometime in the next couple of years. Originally, ChatGPT did not have very many of those connections active at any given time when it was doing a specific input computation, a specific inference. So it only had about 280 billion of those 2 trillion parameters that it was really using at a time. Your brain is much better. You might have heard people say at some point that you only use a small percentage of your brain, and that's largely been debunked at this point. At any one time for any one task, you might not be using all of your brain for that task, but we know that your brain is constantly passing information all the way around, and you're actually pretty efficient in using large portions of your brain throughout any given day. So you are using a huge number of neuronal parameters at any given time, but ChatGPT is starting to catch up, especially from where it was not so long ago. If we look at memory, we now have managed to integrate short-term memory and multiple different working memory systems into some of the newer AI models. So they're actually able to hold in their memory an image or a couple of images, more numbers, and larger blocks of text. It's not the same as yours. It's different. All of this is different, but it's getting more powerful, and that means it's able to do more complex tasks. Executive functioning, we are starting to create, through a variety of different ways, a modular ability for AI to mimic many of the different executive functions that you have. And so the idea is eventually some of these agents are going to be able to switch between different tasks, or you'll be able to access multiple agents with one master agent in a single task, and that will be able to do something very similar to you passing information to the different processing centers in your brain to do different types of manipulations. And we can see that the efficiency is getting better. I said you use about the energy for one light bulb. And so if we compare it to the human performance, the older version of ChatGPT, basically a single query would take up about 9 minutes of your normal brain activity. So you ask it a question and it uses about the same energy as 9 minutes of thinking for you. The newer ChatGPT models actually have become more efficient. So if you ask it that one query, it's only going to use up the same amount of energy you use in 1 minute. They're getting more efficient. And it is true that we will talk about this in a minute, that there are energy concerns with AI, but it is worth noting that the models are actually getting more efficient and powerful in what they can do with a smaller amount of energy. All right, so let's dig a little deeper now. We've talked about what AI is, and I've given you an idea of how powerful it is. We sort of have a model in our brain about what it could sound like to interact with some of these AI systems. How in the world were these made and put together? At the most basic level, they have 4 components I want you to know about. And I think that any AI system that you ever want to use, you need to know at least these 4 components. You need to know what is the design purpose of the specific AI model that you're looking at. And that might be different than the stated purpose. You need to know how the AI was trained. Different training methods are going to cause different types of problems, biases, and performance. You need to know the data that was used. If you don't know the data that was used, there is no way you can really interpret whether it's a good or a bad model. And there has to be human oversight at every stage in the AI process, and you need to know what that looks like. If you don't know that there is human oversight, then you can't responsibly use a model. Now, what the purpose, the training, the data, and the human oversight look like is going to vary from model to model. So let's look at each of these components. We'll start with purpose. At the most basic level, AI has historically been based on prediction. If I give you this information, can you predict who's going to do well on these tests? If I give you this information, can you predict which image is a cat and which image is a dog? And some examples of things we've used it to predict in the past are who is a high recidivism risk if we give them parole. That's actually something that AI systems have been designed to predict, okay, which of the following people is a high recidivism risk? Who should we consider? Who should we not? Classification is the idea that we are going to take one big pile and separate it into 2 piles. So we take all the pictures, separate them into cats and dogs, or 3 piles, cats, dogs, other. An actual example of classification AI systems are insurance companies are using them to flag which claims have merit or don't have merit, to rapidly go through the large number of claims they get and say, okay, these are the ones we're going to spend our resources on, these are the ones we're just going to deny outright. Generation is the idea that the AI is trained to do a specific task, copy this image, look at the starting number and come up with a picture in this style, and then after training over millions and millions and millions of iterations and optimizing to be really good at that task, you take away the training wheels. You no longer give it any kind of input. You just give it a blank slate and see if it can create whatever it was trained to identify or classify in the first place. And so it can do that with music or sounds or vocal quality or any number of other things. All right, we'll talk more about that because you probably have some thoughts. But let's move on to training. Broadly speaking, there's 3 types of training. There's supervised training, unsupervised training, and then reinforcement learning. Supervised training is where the AI has various sensors and it can basically see how the human performs or see what the human sees when the human's performing, and that allows the code, the algorithm, to be modified on the fly so that it can perform the task better. And so each time it tries the task, it uses what it just observed to try to manipulate the data and do the task a little bit more like whatever it's observing. Unsupervised learning is where you just give it millions and millions of examples of something, like Where's Waldo? We give it every Where's Waldo ever made. In fact, we create millions of additional copies of different Where's Waldo that have been shuffled around. And we tell it to find Waldo. And at first, it takes it 2 hours and it finds 50 Waldos, and they're all wrong. But eventually, it takes it 1 hour and it finds 3 Waldos, and one of them is the correct one. And then we do it a few more millions of times with positive or negative feedback each time. And then it gets to the point where it can identify Waldo every single time in 0.2 seconds. That's unsupervised learning. Data heavy, training heavy, but powerful. Reinforcement learning is the idea that we code a point system into whatever model we're looking at so that every time it successfully does something, it gets points, and every time it fails, it loses points. And it's very similar to what you do with something like clicker training with a dog. Because of that constant desire to optimize its code to get the points, it will modify what it does much, much, much better than if we just did something like unsupervised learning. Data sets have to be huge when we're doing all of this, and they also have to be standardized in certain ways. We can't just dump random data in. So the first thing is they have to be big. If you just want to predict a single variable, like what letter comes next, you might need like 500 examples of words. If you want to predict something like which image is a cat and which is a dog, you might need something like 10,000 images. If you want to get a car to drive itself, you would need millions of images and hours and hours and hours of collected video from multiple sensors. It's also important that these data sets are representative. So that means that they have to be accurate. They can't have bad data, or that's going to throw off all our training. The data has to be reliable, and it has to be representative in that if I'm looking at a population that has 50% men and 50% women, but my data set is 90% men, it's not going to train appropriately. The final model I have will be really good at predicting things if I give it a similar population of 90% men, but the second I look at the actual population I want to use it in, which is 50-50, the entire model might not work, or it will give wrong answers. And so that's this balanced. And we also want diversity. If you want to have a model that will generalize to the general population you're interested in, then you have to represent all the different subgroups in that population. If you only collect people from one ethnicity, you can't expect it to generalize to all of those other groups. Finally, you have to have consistent formatting and labeling in your data sets, and this takes a lot of time. So let's say you have a large number of pictures and you want the AI to learn which ones are men and which one are women. You're going to have to label the men and the women so that the AI can actually figure out when it was right and when it was wrong. And that means someone's going to have to go through, look at each picture, and label them. You might also want to label specific features that are associated with men and women, things like maybe Adam's apple or other things like that, hairstyles, etc. And they're going to have to be consistently formatted. So if they're all facing forward with the same resolution, the AI is going to be able to use that pretty well. If they're all in different positions and poses with different numbers of people in the picture, some of them are profile, some of them are looking at you, they're different resolutions, they're different color scales, that's going to be a very messy model, and it's going to be very hard for the AI to learn. This site just has, this slide has a number of places you can go to look at actual AI data sets that you can download and access and use that are pretty awesome. I'm especially appreciative of TalkBank, which is a database of different corpuses for things like phonemes or stuttering language or any number of other things. Aphasia Bank, which has samples of aphasia language. And some of those have already been coded in ways that are AI friendly. And so you can actually go and access large data sets already that can be used to train specific AI models. The last component we had was human oversight. Human oversight is a complicated thing, but when we're talking about the actual AI models, there are a few common ways human oversight is actually built into the model. The first one is during the training process. Humans are often a part of the training process at some point, looking at the specific output and saying which ones are good or bad, or rating the output in some way. But human oversight also comes at the settings level. So you are accessing something like ChatGPT or Gemini or Copilot, and you go into the settings and you can say, I want it to be more creative or less creative. I want it to have more formal academic writing, or I want it to have more casual speech. I want it to be more creative or less creative. You can also say, don't save all of my chat history and data, which is then going to modify the types of output it has. You also have hidden rules in every single AI system, and these are constantly being implemented. And instead of changing the actual model, this is basically a set of filters that goes into place based on the output. So you enter data into the model says, okay, I'm going to answer this person's question. They asked how to make a bomb. Here's how to make a bomb. We don't want the AI doing that if we're a large company like Microsoft. And so what ends up happening is they put these rules in place, and these hidden rules say if someone asks about something dangerous, then you say, I cannot provide information on that topic because it's dangerous. The problem is that these hidden filters, as they're not known to us, could easily produce any number of different biases. And while theoretically lots of them are there for humanitarian or incredibly positive reasons, like protecting the public good, it is also completely possible that people put in place filters based on their personal biases. I don't want you to say anything at all about this particular religion. I don't want you to say anything at all about this one particular political view, or I want you to only say things that negatively represent this population. And if those are in place and you don't know about them, it means that the output you're getting is going to be questionable. So the other element of human oversight is after we have put information through the model, we have to audit it regularly to say, hey, are the results we are getting reliable? Does it give us the same results? Are they valid? Is it accurate? And if we do these audits, we need to do it pretty frequently, because what will end up happening is at some point they're going to update the model, and after the next update, the entire model might stop working the same. Now, the data, the training, the purpose, and the rules all go into a black box. So if you've ever heard people talk about black boxes, that's the idea that your phone is a black box, your television is a black box, this microphone is a black box, your mouse is a black box. They often actually happen to be black boxes. If you're an Apple fan, they're often white boxes, but they're still these boxes with buttons. And when you push the button, something happens. Now, what happens depends. Maybe you want to turn on the TV. And all of us know if you push the button, you turn on the TV. Very few of us know how the TV actually turned on. When we pushed the rubber button, it pushed against some sort of a mechanical thing that caused a change in a circuit, that sent a signal to a circuit board that did something that turned on the TV. And that is why it's a black box. We see the button and we see the output, but we don't know what's going on inside, or at least your average person doesn't. And the problem with black box systems is unless you can open them up and see what's actually happening, and unless you have the ability to interpret what's going on, they're not reliable or consistent. They're not evidence-based, because you have to be able to actually explain what's going on inside the box and predict the results. And if you can't accurately predict what's going on or why it happened, that can be really, really problematic, especially in healthcare and education settings. So black boxes lack transparency, they lack replicability, they're not identifiable, they lack explainability, they lack accessibility because it's hard to manipulate or edit the things inside of them. Often we don't understand the causability, what the underlying etiologies or mechanisms are. And again, they're not always predictable. So that is an issue. It's a big issue. Now, I'm going to stop there before I move on to the next part. And normally, if this was a live lecture, this is where I give you a chance to ask me some questions. You could feel free to come up with some questions and email them to me. I am more than happy to answer them. You can go on to my WSU email address on the website and email it to me there. The next section we talk about is going to specifically be talking about actual applications in CSD, communication sciences and disorders, and healthcare. And there's also going to be a little sort of game that we do when we come back.